Is Nicolas Coloma, and this is my presentation for my project of data mining called Assessing Space-Time Variability in Solar Irradiance Processes. So let's talk a little bit of what we're going to do, but let's first talk about the data, which that's going to help us motivate our method. So we will be focusing on a data set of 17 solar panels that are located at the Unoue Airport in Hawaii, and we're going to get 1 second measurements for a range of like 3 months. This figure shows like the geographical location of the sites, and as we can see, there are sites that we are like clearly more geographically close to one another. So the data we'll be obtaining is data of like global horizontal irradiance, or GHI, which measures the amount of sunlight absorbed by the solar panel via the sun and also through like the reflection through other surfaces. We're gonna do a transformation of this data, but it's just taking the log of GHI over the expected GHI under clear sky conditions, basically. And that is what we call the LCSI data. So the following picture depicts the log clear sky irradiance data of all 17 sites during a 5-minute interval in a particular date of the summer. As we can see, even though like the time series seem very similar to one another, there seems to be some sort of like lag between the time series. For example, if we take two time series, the two sites, DH3 and DH4, which is our like solar panels are like geographically close to one another, we see that like their time series which show that like the GHI process are very similar. So one thing that researchers are always trying to do with solar data is like try to do modeling or prediction. However, that it's hard when we cannot analyze our data properly. What are we saying about this is that like just by looking at this picture, which is assuming 5 minutes of data of just one day, we can see that there is some sort of like time deformation between the time series. There seems to be a lag in between that, and this, for example, can be caused for a cloud that passes through one of the sides, and it takes a while to cover the other side. So even though like the sides are close to each other, they might be exhibit what we will call hereafter as phase variation. So this phase variation is something that doesn't let us analyze the data properly. So what we could propose now is an exploratory data analysis tool, a method, which basically consists of, in every data that exhibits this sort of like phase variation, perform some sort of like algorithm that aligns our functions first before doing any sort of analysis. So what we're going to use now to like showcase our method is clustering, for example, which is a technique that is used a lot, and like a lot of scientists will like to have in hand. So this is the idea of like what we're gonna do. We're gonna perform hierarchical clustering using just the geographical distances between the sites. That is, we're gonna cluster sites that are like geographically close to one another, because what we would expect is that like if two sites are like geographically close to one another, their measurements of GHI should also be the same. And like the only thing that should like affect them a lot is like this type of external factors, such as like, for example, as we said, cloud coverage. Then what we're gonna calculate is just like the L2 distance, which we're gonna define later again, between each one of the 17 sites, and we're gonna perform clustering again. And we wanna show that that result is not gonna be as better as if we first did these time alignment methods in our time series and then calculated the distances to perform the clustering. Once we have these distances of cost, we're going to compare the clusterings utilizing the adjusted Ranth index, which is a metric that is particularly robust when comparing two hierarchical clusterings. And then finally, what we want to do is we want to compute a function that calculates this difference between two sides, but based on some geographical distance, to show showcase a little bit of like the spatial time dependence of the process. So let's begin by defining a little bit. So the L2 distance is just the normal L2 distance between two time series. And then the first algorithm we're going to use is called dynamic time warping. So DTW basically searches for a realignment of the time series that minimizes a certain cost function. That is, we're gonna trying to minimize the L2 distance between like realignment of the index of each time series, that it's gonna like allow for them to like align as best as possible. So for example, here in the left, there are two time series that are like shifted. If we were just to calculate the L2 distance between them, we would get a result that is not really representative of like the difference between the two. But as we can see with dynamic time warping, we align the series first, and then we calculate the L2 distance, which gives us a more accurate representation of the real difference between our two data time series we have. So for example, this will be how dynamic time warping would look like between sites DH3 and DH4. We're also going to use another time alignment algorithm that is implemented by us, which is called the best shift algorithm. And the idea behind this one is very simple, because it's very similar to DTW, and the difference is like the time deformations we allow now are limited simply to like translations of our both time series. So we translate one another up to a certain constant, and we capture where like the L2 difference between the series is minimum, which is when they are aligned in theory. And finally, to assess spatial dependence, what we're going to do is we're going to get a function that calculates the cost between the series based on their geographical location. And for this one, we can use the L2 distance, or we can like realign the time series first and then use the L2. And that's, for example, what is called like the DTW metric. So we will realign them using DTW and then calculate the L2 distances. So let's get into some results. This is just a hierarchical clustering of like all 17 sites based on geographical distance, and we chose to take k equals 3 just as a visual representation. So this is like the representation of the clusters when k equals 3. And we can see that there's like a clear demarcation like to the left, kind of like in the middle of our spatial like locations, and then there's this side AP7 in the top right that seems to be like an outlier. Now we perform the same hierarchical clustering, but only taking the L2 distance between the time series, and this is the results we get. As we can see, there's a clear distinction between these clusters, because for example AP5 belongs to two different clusters, then AP7 is not on like an outlier in the second cluster anymore, but now AP6 is on its own, and this reflects in like a low adjusted rand index of 0.76, whereas the rand index can go from 0 to 1. This is the clustering now after we perform DTW, and then we calculated the distances between the curves. And as we can see, the clustering improved. The clustering colored in black is the same now between the two, and then the only thing that is different is that like the side AP3 belongs to a different cluster. But as we can see, and the same happens with the best shift algorithm, but as we can see, performing this alignment of the time series seems to have like a significant improvement when we talk about making clusters. So now we perform this clustering, as we said, just taking the L2 distances of the time series, then aligning them via DTW and taking the L2 distances, and then align them with our best shift algorithm. And these are the results that we were able to get. As we were able to see, accounting for like phase variability in either via DTW or the best shift algorithm does improve the clustering accuracy. Then some other results we get is that like if we calculate this gamma function of all these three metric as a distance of time, we are able to see what we wanted, that like the distance between sites gets bigger as the geographical sites grow in distance between them, as the sites grow in geographical distance between them. Sorry. And this is very important in the realm of like spatial temporal statistics because it helps us see how the process develops in space and time, and it will be, for example, useful for predictions lying ahead. And as we can see, all three methods were able to capture this spatial dependence. And the only thing is that it seems that with the L2, the cost seems to be more non-linear, whereas with DTW and shift, that point cloud seems to be a little bit more linear. Anyways, the conclusions we're able to get is that using the DTW and our best shift algorithm to eliminate or account for this phase variation actually improve our clustering accuracy between sites. Our function gamma was also able to capture spatial structure in a dataset, which is what we wanted. And we also see that our process exhibits different like variances and different structures in different times of day. And this can be explained because in the middle of the day, say 9 to noon or noon to 3, there's more irradiance in general, so like the variance of the process could tend to be higher. So as we can see, this method that we just showed is proposed as an exploratory data analysis technique or EDA technique in the pre-processing stage of data mining to improve and get more accurate information or extract more accurate information from our data. Some other next steps we can say is like after, for example, we got our point cloud of gamma, that it was like the cost between two sites based on the geographical distance, we can feed a semi-variable model for later kriging or spatial prediction. That is, we could predict the log clear sky index day observations on places where we don't have a solar panel, and therefore we can use these results to make more informed decisions in, for example, determining suitable locations for introducing new solar panels, which will like up to some extent optimize and like improve the real reliability of solar energy as a renewable source. Then we have just like the reference we use for this project, and thank you very much.